Hello, my name is Jorge Cabrero. Currently, I am a student of the master's degree in computer science at UAP. I am very passionate about the field of artificial intelligence. Particularly, I'm really interested in daily life tasks that can be improved thanks to AI. Today, I want to share with you a first stage of the work that I've been doing. Very soon, I will present the complete work in the form of a master's dissertation. The title of this work is as shown: A First Approach to Food Composition Estimation, an Image Classification Problem. And before proceeding, I would like to thank for all the support received by Dr. Ivo Pineda. Without it, I wouldn't be presenting this work here. The contents that we are going to review are shown in the current slide. We will start with a small introduction. Then we will follow with the state of the art, then the objective, methodology, results, and finally the future work we envision. All research starts with a predicament. In this case, the fact that globally food-related degenerative diseases have increased dramatically in the last decades. Food and diet guidelines promoted by governments and health agencies haven't had the desired effect on reversing these trends. One of the principal explanations is that guidelines are hard to follow or are unclear. Deep learning algorithms can help to make easier for people to follow dietary guidelines using technology available to them. In this work, a first approach is proposed to solve an early stage of the entire scope of the problem, which is the estimation of calories and nutrients in food based on their image. Calorie counting is one of the two major components in almost all issued health guidelines. Research has shown that restricting calories helps reduce weight and increase health markers such as blood pressure, insulin resistance, cholesterol levels, liver health, etc. The other major component is nutrient density of food. It is well known that the body needs certain nutrients to be healthy, and that these nutrients are only available in food and can't be obtained elsewhere. Therefore, our health depends on a given number of calories and a given amount of nutrients. In order to stick to the recommended values, each person should first know the composition of a lot of food, and secondly, they should know exactly the amount they are eating. Both aspects are difficult and impractical in a modern lifestyle. If only there was a way to easily recognize, access, and measure food composition without actually weight it or search for it, that would mean a major step for achieving better public health around the globe. In this work, we believe that computer vision, paired with deep learning algorithms, can achieve exactly that. By just taking a photo with a cell phone or any device of the food that we are about to eat. Before going deeper into this, we first need to check what other people have been doing in this subject. Currently, there aren't many works on the subject in question. However, tech giant Google have already started to research and develop in this matter with its leading scientist Kevin Murphy. They already have developed Im2Calories, which is an app that can count calories from a low-resolution photo taken with a cell phone. It only works in 30% of the cases, but they are improving it with people inputs since 2015. The model is not open to the public, but it is based on a convolutional neural network. Then we have Yang Chao Liang and Yanhua Li from the East China University of Science and Technology in 2017 created the ECUSTD database composed of almost 3,000 images of 20 categories of food. Also, they introduced a CNN architecture for image classification and segmentation of food in order to estimate food calories. Simon Mesgek and Barbara Seljak from the Information and Communication Technologies Department of Slovenia developed in 2017 the NutriNet, a CNN architecture that they claim to have 94% accuracy in some food datasets. Only classification. And Xiongwen Wu et al. From the Living Analytics Research Center of the University of Singapore compiled a database, FoodSec 103, of 9,490 images with 154 classes and segmentation masks. We can conclude from the work cited above and some others not mentioned that the problem of food recognition is challenging due to the nature of food items. Foods are deformable objects, which makes the process of defining their structure difficult. None of the works reviewed so far have tried to estimate nutritional value on top of calorie estimation, so it seems that there is a lot of room for improvement and the problem cannot be considered solved yet. The objective. The problem is complex and it requires two main treatments that need to be combined. The first one is pure image classification, for example, classifying foods based on the entire image they appear on, and the second is object recognition and segmentation. In this work, we focus on image classification only. We believe that the correct identification of food type is the first step for an accurate food composition estimation later on. This gives us our objective to develop a first approach for the complex problem of food composition estimation based on computer vision plus AI. For the methodology, we choose three architectures to test food classification: the Google Net, the BGG16, and the mobile net. The decision behind testing Google Net seems obvious. The model has the lowest count of parameters of the modern architectures, paired with a great accuracy obtained in the ImageNet challenge. On the other hand, we chose the VGG16 model due to the simplicity and elegance of the architecture combined with its low error. Other architectures, such as AlexNet and CFNet, were left aside due to the high number of parameters in the model together with a higher error rate. The ResNet model was left aside too. This time, the decision was due to the fact that the model has 152 layers, and the size of the images is difficult to fit to the model. Therefore, we should have used the ResNet 18 model instead, which has lower accuracy than GoogleNet and BGG16. GoogleNet and BGG16 were the first and second places respectively in the ImageNet Large-Scale Visual Recognition Challenge in 2014. GoogleNet has 22 layers and BGG16 has 19 layers. Both architectures are big and slow to train, but fast to use in predictions once the training is over. MobileNet was also chosen to test the accuracy of the classification task. The MobileNet is part of a family of mobile nets designed also by Google to effectively maximize accuracy while being mindful of the restricted resources of an on-device or embedded application. For the datasets, we mainly use two. The Food 101 dataset, formed by 101,000 images of 101 food classes, gathered by Bossart and Company for their work in mining discriminative components with random forests. The other dataset we used is the ECUSTD dataset, gathered in the East China University of Science and Technology. This dataset is formed by 2,987 images of 20 classes of food. For short, we are going to refer to this dataset as ECU from now on. The two datasets we chose are fundamentally different, as we wanted to test the CNN architectures in these opposed scenarios. Food 101 presents complex dishes with many components, like Caesar salads, baklava, beef tartare, ceviche, filet mignon, fried rice, etc. On the other hand, the ECU focus on simple shaped foods like apple, banana, bread, egg, mango, kiwi, pear, etc. Images in both datasets were treated to fit the size 224 by 224 pixels, which is the size used in the most popular CNN architectures built for the ImageNet challenge. The treatment used to resize the images was a bicubic interpolation over a 4 by 4 pixel neighborhood. The language used was Python with CV2 library. We made some changes in the fully connected layers of all three architectures before training them with the food images datasets. For BGG16, we changed the number of neurons in the fully connected layers. Originally, the architecture has three fully connected layers of 4096 neurons each and a final output of 1000. We changed the number of neurons to 512 for the three final layers, and the final output was changed to 20 for the ECU training set and to 101 for the Food 101 training set. For the GoogleNet and MobileNet, we only changed the number of neurons in the final output layer in order to match the number of categories in both databases. The three architectures were trained on both datasets, but for the ECU dataset, we used two techniques for the training: transfer learning and full learning. Given that the Food 101 dataset is considerably larger, it was only tested with transfer learning. The transfer learning technique applied in this work was to freeze the convolutional layers of the network with the weights trained with the ImageNet dataset and only train the fully connected layers for 100 epochs. The full training technique trains all layers, including the convolutional layers, with the selected dataset for 100 epochs. The loss function used in all the experiments was cross-entropy loss function, and the Adam step optimizers was used in most of the experiments, except for one where stochastic gradient descent was used. The validation method used across all experiments was a 5-fold cross-validation. The experiments were carried out using Python's library PyTorch and run in Google's Collaboratory and web server. The results. From the results in both tables, it can be seen that for the ECU dataset, a very good accuracy can be obtained with transfer learning in two of the three architectures with relative low training times. BGG16 has the lowest accuracy with both transfer learning and without it. It's important to point out that BGG16 is a model with more parameters to optimize, and that's why the training times are the largest in general. MobileNet and GoogleNet didn't improve the accuracy a lot by making a full training without transfer learning. For the Food 101 dataset, the highest accuracy achieved was obtained with GoogleNet. Second and very close was the MobileNet, and BGG16, as with the other dataset, failed to do a decent classification. We can conclude that food classification using transfer learning and well-known CNN architectures can be satisfactorily achieved in cases where the food classes are simple and isolated in an image. For example, images of fruits. In the other hand, when complex dishes are taken into consideration, the recognition drops dramatically. However, a 60% accuracy for complex dishes without any kind of prior segmentation or object detection reflects a positive result, because it means that with proper segmentation and detection algorithms, accuracy can improve a lot. Conclusions. Further experiments need to be carried out with the BGG16 architecture because the default experiments achieved a very low accuracy. Changes in the fully connected layers, epochs, optimizer, and kernel sizes can be tested in order to see if the accuracy can increase. The results of the experiments confirm our assumption that this approach can be a first step for a full food composition process. Next steps could include object detection and segmentation algorithms, paired with the image classification methods mentioned above. Furthermore, even though a lot of improvements have been done in deep learning with CNN algorithms, for food composition estimation, exists a real challenge to construct a model that can classify food correctly, and one of the major setbacks is that there are not many datasets on the subject. Many of them are small or they represent small classes of food. Also, many food dishes have irregular shapes and wide color ranges, and that represents a very complex problem to solve even today with the most robust of architectures. Future work can focus too on obtaining datasets of regional foods, as we believe also that regional foods images can increase the accuracy in any model trying to classify dishes of a given country diet. Thank you very much. That's all.